Welcome to qnawire.
The radial probability density for the 2s state of the hydrogen atom. This is the wave function we used in problem 38, where for the radius of 4 times the Bohr radius, I found the correct energy for the hydrogen 2s state. But in this problem, we're going to find that the most probable location is actually closer to 5.3 times the Bohr radius, unlike the case of the psi 1s state where the Bohr radius is the same as the most probable position. So that's kind of the point that this problem wants you to uncover through calculation. So it's going to want us to find the maxima and the minima of the P2S probability density function. So we have to calculate that. So that's conceptually, that's a thin shell in three-dimensional space, and you're finding the probability of the electron being found on a shell given radius. So that becomes 4 pi r squared times the square of the wave function, which is the first equation we have here. You can just square it because it's a real value function. You don't have to do a complex conjugate. So it follows from that P2S R equals 4 pi r squared times that, which ends up equaling 1 over 8 a naught cubed is r a naught squared r squared e minus r a naught. This is just plain straightforward multiplication. So that is the first thing. I believe part B is now we want to find the minima and maxima. So that's when this function, the probability density function in radial terms, well, first we'll find the function, then we'll set the derivative to 0 to find the maximum and minima. So if you take the derivative of the equation we just derived, C1, let's see. So the constant stays out front, but it's going to pull out more constants of 1 over a naught. So if you were to do the derivative out, you'll find that the first coefficient out front is a naught to the 5th power times r divided by a naught r squared minus 6 a naught r plus 4 a naught squared times r e. So that's just a straightforward doing the derivative of the equation that we derived in part A. So then we have to find when 2SR equals 0. So it's 0 equal the equation we just found. So we're finding the values of R. So we can do this by inspection. So one of them is R equals 0. It also goes to 0 when R goes to infinity. And looking at this, this term, if that equals 0, the whole thing goes to 0. So that is R equals 2 times A naught. And then if you look up here, so that's 1, infinity is the other. Let's see, 2A naught is slightly above 1. So that's that one. So these are the minima. And then this is a quadratic equation. So those are going to be the maxima. Now you might want, it's one thing to have the graph here, but you might want to know why you can be certain that these are the minima. So the probability density function has to be positive. So R equals 0 and R equals infinity have to be minima. And then if you do the quadratic formula on this middle term, you would find that R is going to equal 3 plus or minus square root of 5 A naught. These are the other two roots. So that is about 1.2 A naught. See, so we know the 3A naught minus square root of 5. Sorry for the pause there. A naught is less than 2A naught, which is less than 3A naught plus square root of 5 A naught. Because this is 1.5 something, roughly, this is 2 some, well, it's exactly 2, and this is roughly, it's approximately 5.3. So since 0 is a minima, the only thing after a root after it for the slope being 0, this one has to be a maxima, which means that this one has to be a minima, which means that one has to be a maxima, min. So I believe D wants to find maxima. Which we had just proved. So then it wants to know which is highest probability. Well, in that case, we have to go back and use this equation. So we're not using the derivative equation anymore. We just use those to find the locations. So we know what the maxima are now. We have to use this equation to find what the actual value is for the probability density function. So then we have P2S R equals cubed 2 minus R A naught, that is squared R squared E minus R A naught. So all this is plugging in these R values and finding out which is higher. You can see I will have A naughts canceling out. You end up with 1 over 8 A naught. And then the values are two cases. It's one or the other. So for R equals 3 minus square root of 5 A naught P2S R equals that one is probability 2SR equals 0.19 1 times 1 over A naught. So you can tell just by looking at that that this is the value for the maximum, and 3 plus square root of 5 A naught is approximately equal to which is what the problem was looking for. So that's greater than 4 A naught, which is the radius the Bohr model has for the n equals 2 state, which correctly gives the energy level. It's just the most probable state. It's 5.236 times A naught for the n equals 2 state. And this term here, probability, doesn't have dimensions. It's just a number. This is a scaling factor because we're doing R over A naught instead of just radius. So it's the coefficient in front of the 1 over A naught that gives you these probability numbers on the vertical axis. But so that is 5 plus the square root of 5 A naught is the most probable location, and that seems to be all this problem is looking for.